Okay.
So now,
how do I?
yeah, the pointer is here. Okay. Now we have Julien Hegel on reionisation time field reconstruction and Mollet exclusion applied to WDM.
Okay, thanks. So hi everyone, my name is Julien Hegel. I come from Strasbourg and I'm a PhD student. And today I will speak about the epoch of reionisation and the large-scale structures. Okay, so first, what is the epoch of reionisation? And in fact, the epoch of reionisation is a period where the universe transitions from a cold and neutral state to a not an ionized state. It is due to the first sources of ionizing photons, so, such as stars, galaxies, and so on. So during this epoch, the neutral hydrogen emits a radio signal. It is a 21 centimeter line, and we will observe it with future radio telescopes, such as the Square Kilometre Array. So here on the images, you have typical 21 centimeter maps, where you can see the whole temporal evolution, so the time is like this, okay, of this signal. The important thing here is to remark the white region that are the ionized bubble of hydrogen that will appear somewhere here. They will grow, and eventually they will merge together until all the intergalactic medium get reionized. One thing to realize here is that this whole evolution can be described with one single picture, and this picture is the reionisation time field. So what it is in fact a distribution of time where each pixel here describe where the value of each pixel, represents the time of reionisation of this given pixel. This field is really interesting to study because it contains a lot of information. First, it describes the whole history of reionisation for this map of that could be an observation, for example. Another example is that the minima in red and the maxima in yellow are related to the reionisation seeds and the last region to reionize. It is likely the densest and emptiest region in this map. Nevertheless, this field is not unobservable, so we need to find a way to recover it from the observations. This is what I try to do with my study here. I want to recover the reionisation time field from the 21 centimeter map here. So I will use machine learning method to do so. And to this purpose, I need a large data set that I will build with the 21 centimeter fast simulation code. And then I implement and train a convolutional neural network to just infer once again the reionisation time field from the observations, so the 21 centimeter maps. Here you have just the parameters that we have used for the simulation. So here it is a classic lambda CDM cosmology. And we have selected 18 redshifts that will be the redshift of observation. On the right, you have the architecture that you have used. It is a UNet architecture that is designed to construct an image as output from another image as input. Here, in my presentation, I will talk a lot about predictor. And what I mean by predictor is a trained convolutional neural network at a given redshift. Here, we have 18 redshifts. So at the end, we will consider 18 predictors. So once the predictors are set and trained, we can just make prediction. And here you have a typical example. On the left here, you have a 21 centimeter map at redshift 11. We pass it through the predictor trained with images at redshift 11, and we get the image on the right, the prediction of the reionisation time field. Okay, so first thing that we can say is that it works, and that's surprising because actually the 21 centimeter map describes the physical state of hydrogen at a given instant of the universe history. And the reionisation time field is its whole evolution, so past and future. So now we have just a predictor capable of predicting when a pixel in this map will reionize in the future or has reionized in the past. Now we want to compare the prediction with the ground truth given by the simulation. And here what we can observe is that the prediction looks like a smoother version of the true field. And in fact, the predictor here have some difficulties to recover the extrema. So now we can wonder what is the behavior of such a predictor when it is trained with another redshift of observation, and especially, is there a best observation redshift for such kind of prediction? So this is what I try to summarize with this slide here. In red, you have the coefficient of determination. In respect with the redshift of observation, it is defined just here, and it is just an estimator of the predictor performance. On the left, for the low redshift of observation, between 6 and 7, let's say, here we have a low performance, and that's not surprising because on the observation, we have a low signal fraction because typically we have no signal inside the ionized bubble that became too large for this range of redshift, okay? Then, at redshift 11, you have a peak here, and in our simulations, it looks like it is the best compromise between the number of ionized bubbles that is sufficient to locate accurately the reionization seed, and the size of these same bubbles that is not too large to lose too much information. Because once again, if you have the bubbles that get wider, you will lose information inside the bubble where there is no signal. So we cannot predict anything from nothing, basically. Okay, so at larger redshift now, the performances get slightly worse, and it is basically because we have fewer ionized bubbles in the observation, so we can locate fewer sources. Now we just want to leave the perfect world for a few seconds. Here we took the SKA characteristics and computed typical instrumental effects that we can have with it. We added it to the data set, and we get images just like this. Here, on the prediction, on the right, we can see that the large-scale structures are well represented here. Nevertheless, the small scales and the intermediate scales are completely missing from this prediction. So that might be an issue. And the last thing for this first part that I want to show you is a fraction of neutral hydrogen. So basically, you have the ground truth in black, and you have the prediction for the fraction of neutral hydrogen for prediction with and without noise in blue and red. So in red, when you have when there is no noise, the predictor just gives a satisfying reionization history. But when you add noise to this to the observation, typically, the predictor will start the reionization later, and it will finish it earlier here and there. Okay. Then, at the end of this first part, we had some questions in mind. One of them was, what happens when we give some data to a wrong predictor? Because ideally, data given to a predictor with the right model should give the same reionization time for no matter the redshift of observation. You have an example on the left for redshift 8 and 10, and their prediction here. Here, the two predictions look similar, yet they are not identical. And then we can wonder, what if we notice an inconsistency between two reconstructions at two different redshifts? And then can we use it to just exclude a predictor? This is what I want to do with a warm dark matter model in the following. First step that we have to do is to set a model as reference. Here it will be the cold dark matter. It will basically serve as mock observations. Then by training a convolutional neural network with dark matter models and two redshifts, we get a collection of predictors that will be used later. Here we selected redshift 8 and 11, and you have the four models that we have selected here. Afterwards, thanks to the mock observations, so still the cold dark matter, we infer the reionization time with each predictor, and eventually what we want to do is just to compare the prediction and estimate whether the predictor fits the observation or not. So here we can do that because the two predictions coming from a given predictor model but with two different redshifts should be statistically identical. So now I want to check this auto-consistency using the isocontours. And in this context, isocontour depicts the interface between the neutral and the ionized region, so the neutral and ionized bubbles at a given time. So here, just on the map, you have example. of isocontour for 0.4 and 0.6 gigayears. And on the right, you have a typical distribution of isocontour for the true field. Here on the bottom, you have the distribution of warm dark matter minus the distribution of the cold dark matter. And what you can observe is that for the warm dark matter model, you have fewer ionized regions at early times, and you have more neutral regions remaining at late times. It is because the warm dark matter model starts the reionization slower than the cold dark matter, and at the end, there is more neutral region remaining, and then it has just to finish the reionization. Okay, so my last slide is this one. The idea here is that for a given predictor, as the prediction should be statistically identical for the two redshifts, we should have the same isocontour for the two redshifts. Then we want just to compare the isocontour total length for the two redshifts. So here we have, for a given predictor, we just take the isocontour at redshift 11 minus the isocontour at redshift 8. And then we just test the autoconsistency of each predictor this way. So here in black, you have the curve for the cold dark matter. And even this predictor isn't perfectly autoconsistent. And it is surprising because in this context here, the cold dark matter is the reference. So we could have expected better from the predictor of cold dark matter. Then in yellow, you have the 7K predictor. It has the same level of autoconsistency as the cold dark matter. And here, that was expected because 7K is a relatively high mass, and then it is pretty close to the cold dark matter. Concerning the red and blue curve, it is for the 5 and 3 Kev. And here it seems to present a larger level of inconsistency between the two redshifts. So based on this statistic, we may exclude these two models. But we need a more quantitative metric to just confirm that fact. This is a work in progress. Okay, so now I think I'm running out of time, but I leave you with my conclusion, and thank you very much for your attention.
Okay, thank you. Are there any questions in Paris first? Nabila?
Thanks for the presentation. I had a curiosity question with respect to the smoothing that you were mentioning. So you specified it in the case of the realistic case, but in fact we were seeing it also in the idealized case with the smaller scale being smoothed. Mm-hmm. So is this I guess a result of the architecture, or is it and how detrimental it is from the point of view of the analysis?
In my experiences, I always had this kind of smoothing when I tried to just recover a feed from the 21 centimeter maps. I tried with densities, just the fraction of neutral hydrogen, etc. But there is someone one day that told me that it isn't about the architecture, because the units actually may have very good results with the small scales, but actually, I tried a lot of things, but I haven't succeeded to just recover these small scales. So I think it is due to the ionized bubbles, because when you have your bubbles here, you haven't any signal inside it, so you lose a lot of information inside the bubbles, and probably it has a kind of smoothing effect in the prediction.
Question in New York, maybe?
Maybe I have one. So are you using a mean square error as a loss function for the unit?
Excuse me?
Are you using like the standard loss function?
The loss function, you mean?
Yes.
Yes. In this architecture here, and what I presented just here, it was a mean square error. But I tried a lot of things, like the Uber loss function, like the mean absolute error, and so on. And actually, the performance, the global performance, were basically the same with all the loss of this, all of this loss function. So yeah.
Yeah, because for things like unit, it's very well known that if you use like mean square error, you are predicting like the posterior mean. So to get these small scales where you probably have a scatter, things like diffusion models or even adversarial network, probably will help you with this.
I'm not sure.
I think might be a part of the problem that you, yeah.
I'm not sure.
We can talk more offline if you want.
The oversmoothing could come from the MSC.
Oh, yeah, I know. Actually, I had this remark a few months ago, and that's why I used a lot of other loss function, but I didn't succeed to just erase this smoothing. I'm still looking for it. I have the plan to just try attention block or GANs to boost these small-scale issues, but for now, I haven't the answer.
Thank you.
Yeah, thanks for your question.
Okay, so let's thank the speaker again.